quickly go through the VLE Moodle site so that you know what is expected from you and what you can see. Anyone had a chance to look at the VLE? Yes? Okay, so on the VLE, if you navigate to your course, you will see that in the start I have provided a short description. It will explain that what we are actually doing in this module. I will also be explaining throughout this lecture. And then for throughout this module we have 12 weeks. We have 12 lectures, and then we have 12 weeks for workshops plus tutorials. By time you will see that we will most probably you will be doing 6 labs at least, and then the rest you will see how we're going with the tutorials, or if we need more labs then we can scale down tutorial and so on. There is a module guide also provided here. I will also go through the module guide. You can read through it, and as I said that I will be the point of main contact. So if you have any problem, any difficulty, you can always reach me out. There is a link to Microsoft Teams. So what I will be doing that I will also be recording this lecture. I will be putting all the content, whatever you have on VLE, I will also put it on Teams if in case this is more accessible. Then you can also post your questions that you have, and I will try to answer them as soon as possible. This is the link to the timetable, which is just a PDF, but there is also a link given here for the live timetable, which you can always see. Normally this class would be at 9 a.m., 9 to 11, and then for 11 onwards until 1 you have a lab. But you can always check an updated timetable. And this is Teams link for online meeting. I'm using currently this link to record the meetings, but if for some reason you're unable to join physical lecture, although lectures are physical, you can always join through the link. Then if you go through the module administration, you will see that again you have a module guide, then you have a guide for the library, that how you can borrow a book and so on. Then there is some information about timetabling, if you have any issues, how to apply for ECs, all the things are mentioned here. Any questions, late submissions, and so on. Now about assessment criteria. So overall this module is 100%, so out of 100%, 60% is dedicated for final exam, which would be 2 hours exam unseen without any book. However, the other 40 part is allocated for coursework, and if you consider coursework as 100%, so out of that there would be 40% phase test plus assignments, and the rest 60% is about logbook. And how to prepare a logbook. If you open this link, this course assessment, you will see that there is a guideline provided on how you can prepare a logbook. So essentially this logbook will contain whatever workshops you're going to do. For the initial 6 weeks, we will be using MATLAB for half of the portion of the course, and then you can use these guidelines and prepare your lab report. You can see that there are different marks allocated. So if you follow these guidelines, then you can get full marks. And again, I have also provided a sheet which shows you that how you will be marked. Okay, and then for week 1, I have just put some introduction what we're going to cover. Right after my lecture, I will also be uploading slides. But if for some reason, if you feel that you want slides before lecture, I can somehow upload it so that you can write on it. But maybe sometimes you will see that there are 1 or 2 slides changed last moment, but I will make sure that I will upload it just before the lecture. If we quickly go through the module guide.
Just make it work.
Module guide will say more or less same things that I have just explained, but it has few more things that you want to see is what are aims of module, what are learning outcomes. So I would encourage that you go through it. It will give you a rough idea how we will navigate through the course. Then, as I said, that there will be 2 hours per week lecture class, and every odd week you will be having tutorial, but it can be mixed with lab, depending on how much. I mean, for first weeks we will not be covering too much content, so maybe we'll combine it with lab, but we'll see as we go. Assessment criteria I have already explained. Then there are some useful links that you can follow, and this is the overall content. I will explain it in today's lecture as well. And then there is timetable and some useful information about core books. These books are available in library. I'm not sure if there is a hard copy, but you can always get a soft copy for there. And if you feel any difficulty, just let me know and I will provide one. Okay. Okay, so now starting with the technical content. As we know that this module is artificial intelligence and signal processing. So you can see that it is combining two domains. One is AI, one is signal processing. And if we go into more detail, the very first question is that what is AI and what is signal processing? If I give a short definition, AI is anything which makes a machine intelligent. So consider your Apple phone. So if you say something to Siri or to Android phone, it can act on your voice and then bring it something. If you say just open YouTube, so it is so intelligent, it is made intelligent that it can capture your voice and then bring something up. So this is AI. And what is signal processing? Like I said, if I'm speaking something, for mobile to understand, it's very important that the mobile can process it. So it means that AI and signal processing, they cannot work alone. They have to work together. Now, the question is that there are two aspects. One is AI supporting signal processing, and the second one is signal processing supporting AI. So I have quickly put some example which will give you a rough idea is how AI is supporting signal processing. So normally what happens that there are a lot of signals, even now we are standing, we have a lot of signal around. And if you, for example, take an example for military, so what they usually do, they want to capture some information and then process it. But there's so much information and they don't want to waste their time. So their first gate is AI. So what AI is doing, for example, if you are looking for a mail, so the AI technique will look for voices which are from mail and then discard all other voices, and then those voices will be sent to signal processing, and then we'll process it whether this is person number 1, person number 2, and person number 3. So this is one of the examples in which AI is supporting signal processing. And same goes for other applications. If we talk about our mobile phone, for computer, Arduino, all these microcontrollers, they have limited space to process things. So if you are giving them too much of data, it is possible that they are unable to process it. So that's why the very first step is to make an AI gate which take the information. If it is useful, if it is not useful, it will throw it out and only send the useful information so that your processor is not overloaded. So this is one of the examples in which AI is supporting signal processing. And the other example is signal processing for AI. Like I said, very good example for the mobile phone, that if you are speaking something, mobile doesn't know what it is. But the very first step is that your voice will be processed, it will be converted into a language which is understood by a mobile phone, then comes the AI. So then the AI will process all those signals and will give you something out. So what does it mean? It means that AI and signal processing, they work together to make system intelligent. Here are some examples, but before example, I have put a line on the top. We can use AI and signals everywhere. It means that this is a very good slogan, that we have signals everywhere, but to use those signals intelligently, we use AI. And one of the examples is about this face recognition. But before that, a very good question is, what is signal? What do you think, what is signal?
Waves?
Yeah, waves, electromagnetic waves. It can be voice signal. It can be temperature signal. It can be anything. It can be images. So normally, like you said, that when we think of signals, it comes like a sine wave, a voltage signal, a current signal. But it can be anything. And as a matter of fact, right now we are standing. We have signals everywhere. So that's why we use some techniques or something to process those signals, to take out useful signals and then process it. And one of the examples is about face recognition. So in this example, what is being done? So we take this image, we process it. In processing, what we want to see, we are probably looking for eyes, teeth, face. So we have different classifiers. So if you open your mobile camera, it will detect your face. Why? Because inside it has been trained to do so. So here you have AI and signal processing both. What AI is doing, AI is probably measuring the distance between lips and chin, eyes, color of eyes. So all those signals are being said as classifier number 1, classifier number 2, 3, and 4. Probably it is looking for eyes, ear growth, and so on. And later on, when you give an image to it, then based on those classifiers, it can read the image and it can detect where is the face. So this was one of the examples. Normally when we say processing, it comes to our mind like we are processing something in Excel sheet. For example, you have student number, so you are sorting them, or if your employees, you want to see their working hours and so on. So those kind of data is actually called structured data, and normally so far what we were doing was structured data. But in reality, we don't have structured data. In reality, we have random signals, we have random images. So it means that we have to somehow work on those real life scenarios, sensor images, and so on, in order to get some useful information. And for that purpose, we need to combine AI and signal processing. Again, following the same trend, signals everywhere. So here's an example for activity detection. You might have experienced that if you have an activity detector or any smartwatch, if you are sitting for some time, it will show you that you are sitting for a long time, it's time to get up. Or if you get up, it will show you that, okay, good, now you're walking or something. So how it is doing that? Again, here it's AI and signal processing. So the very first step is that your device or whatever, it's measuring whatever information you have allowed. For example, you have allowed that it can measure your heartbeat, it can measure your footsteps, it can measure your body temperature, and so on. So it means that you get all these signals using any kind of sensors. So now, once you have the signals, you can perform different processing. For example, you want to see what was the maximum heartbeat, what was the minimum heartbeat, what was the heartbeat when I was running, what was the heartbeat when I was sitting idle, and so on. So it means that we take in the signals, we use them to find the attributes that we need, and then finally those attributes are given to some models which are called AI models, training models. So those models are being trained for some known data. So I'm recording signals, I'm training the model. So the model know now that what should be the limit for example, heartbeat when I'm running. So it means that now this model is trained. And later on, when I am doing a random activity which this model doesn't know, it can detect based on the training that what I am doing. So based on that, it can detect that I'm going upstairs, I'm running, I'm sitting idle, I'm watching television, or anything. So here we are using some bunch of signals to train a model, and then that model is being utilized later on to do intelligent things. Another example is about an autonomous car. So if you have a car which you want that it work at its own, so you need a lot of sensors. Why do you need a lot of sensors? So if a car is moving, so you need a sensor to see obstacles. You need a sensor to watch for traffic lights, to watch for people. And then again, so this is one thing, that you need all these sensors to get those signals. But then you need to train your car as well, that if, for example, you see an obstacle, what you have to do. If you see a traffic light green color, what you have to do, and so on. So based on all these signals, you are going to train your model. So you can see that if this is your guard, you are taking all the sensors. So this is policy. Policy means any rules, any regulation. For example, if you see red light, stop. If you see green light, gone, and so on. So you are training your model, and then it is taking some action and either stopping your car or either giving it more accelerator and so on. And then this is your environment from where you are taking sensors. So again, this was a very good example, but in this we have so many sensors, we have so many signals, and we need processing. So in this case, sometimes we don't need all these signals, but for certain function, we don't need all signals. For example, for speed regulation, we only need speed signals. So it means that we don't need other signals. So that's why we need to use AI and signal processing together. Finally, there is a last example. So imagine that you have number of speakers and you want to build an algorithm to detect based on their voice the name of the person. So the very first thing is that you will take n number of speakers, whoever you want to build algorithm for, and then you will start one by one. So speaker number 1 speaks, then you use signal processing to measure its frequency or to measure its pitch or any other attribute that belongs to the audio signal. And then based on this, you will create a database that, okay, if frequency is this, if pitch is this, amplitude or something is this is person number 1, and then you're going to repeat it for n number of speakers. So now you have a huge database which has classifiers for all the speakers. And then later on, you will use that database for prediction, for estimating or for getting to know that which person it is. So again, you take unknown speaker, you will process it. Why? Why are you going to process the speaker again? Because in order to measure it against classifiers, we need those values. For example, here we have set of variables, pitch, frequency. For example, I'm taking 2. So for unknown speaker, you want to get pitch and frequency out so that then you can compare this with the database and see to which person these attributes are equal or to which person they are corresponding. So based on that, you can get to know that which speaker it is. So in all these examples, you have seen that we cannot use one alone. We have to use them together to do some work. So that's why it is very critical to study both signal processing as well as artificial intelligence. So this course has been divided into 2 chunks. So the first 6 weeks, I will be teaching you signal processing, and then the remaining 6 weeks would be AI.
We covered lab last time.
Sorry?
We covered these topics.
Yes, we will be covering these topics. Yeah. Have you studied these before?
I know, it's going to be very tough. Mathematics, a lot of mathematics.
Yeah, I mean, solving these and equations, yeah, those mathematics are rigorous actually, yeah. So, in terms of signal processing, we'll be covering some basic signals, what are signals, and then we're going to see what are different techniques to process them. And then as part of AI, we'll be seeing that how to bring intelligence into signals and what are different techniques, what are different methods. You might have heard the name artificial neural network or machine learning. These are very common these days, so we'll be going through these techniques to see that how we can use them to make our systems more intelligent. So, coming to our first part of the module, which is signal processing, how to process a signal and to see its underlying concept. So, as I explained previously that what is the signal processing? What is signal processing? So anything that transforms your signal from one form to another form is called processing, whatever it is. If, for example, you are taking a signal, you are multiplying it with 2, this is kind of processing. If you are converting it to any other form, this is processing. So there are some examples. So filtering, decomposition, then like I explained previously, face recognition, speech, feature extraction, and so on. And later on we will see that there are two important concepts: frequency domain and time domain. So normally we see everything in time domain. So if we see that, okay, how things are changing with respect to time, but sometimes it is important to see the frequency side. And why? Because you all know that for a sinusoidal signal, if we say that it has 50 hertz, the one coming from the socket. So in time domain, we cannot see that if it is 50 hertz really. So in order to see exactly if it has only one frequency component, we need to transform it to frequency domain so as to see whether it has one component or more. And same goes for other disciplines. For example, if someone is studying light signal, so it's very important to see that what are different frequency components of light. For example, you can take an example of rainbow. So you have different frequency components. So in order to understand those frequency components, again, it is very important that you transform those signals into frequency domain and somehow analyze it. So again, these transformations comes under signal processing. So now if we go through some basic that what is a signal processing. So in any signal processing, we definitely have an input signal, we have an output signal, and then there is a black box which could be any mathematical function that is processing it. What can be these functions? So for example, if you are giving an input and it is multiplied by 10, what that system can be? Any example? If you are amplifying something, so if you are giving 1 at the input and at output, we are getting 10 volts, so what we call that system is amplifier, right? So this is one kind of system. And then if, for example, you are sending an input signal and you want your system to block high frequencies. So what that system is? You want to block your high frequency signals and want to get low frequency signals at the output. Yeah, it's going to be low pass filter. So again, this system is a filter, but which filter? A low pass filter. Then if you keep on going, you will see you have thousands of systems either in your mobile phone, either in your laptop, which are performing different functions. For example, you can see noise cancellation. So if you wear your earbuds or something, they have feature. So what it is doing, it is taking that signal and seeing that what is mean of the signal and then removing all other noise. So for that we have noise cancellation filter. So again, this is a kind of system. And so on. These systems are not limited to electrical engineering. It can be anything. It can be economical. It can be from our body. For example, if we take an example, we are looking at, for example, I'm looking at screen. My eye is processing those signals. Then it is giving signal to my brain. It is reprocessing it. Then I'm doing something. So all you can see that you're processing those signals. Then ultimately you are doing something. So now here the system is from the human body, and so on. So we have plenty of examples in which we are using different systems in our daily life. So if, for example, we talk about measuring the temperature. So if you are measuring a temperature in a room, so you are giving an input signal to the temperature sensor, and then at the output you are getting a voltage signal to see how much it is. Normally this is how temperature, and then you try to calibrate it. So again, this sensor is system here. So as I said previously that we can study these signals either in frequency domain, either in time domain. Sometimes you will see that it is useful to see them in time domain, but sometimes either for mathematical ease or for visualization, we convert them into frequency domain. So normally the voltage that we take from this socket, we say that it is 220 volt RMS 50 hertz, right? But because of so many loads, different kind of loads, it is not always 50 hertz. There are several other components in those signals, in that 220 hertz. So if we say that we have 220 volt RMS 50 hertz, so sometimes you will see that it also has 100 hertz, 150 hertz, but looking at time signal, we cannot read it. So we need to convert this signal into frequency domain to see what are frequency component, because we only need this component. So if there is any other component, our devices are not manufactured for those. So it's very important that we need to see that if, for example, our signal is clean or not. And if it is not clean, sometimes you will see that your device will make some noise, or it will heat up or something. So that's why frequency domain is very important. And if someone is from power system, he will know that we say these things as harmonics, that these are unwanted signals, and we need to understand that. So that's why we need to switch between domains for our ease or physical interpretation. Okay, so now moving further, there are different kind of signals that we're going to study. So we have continuous signals, we have discrete signals, which are also called digital, and continuous are also called analog. Then we have periodic signals and aperiodic signals. So let's move towards the continuous signal. So what is a continuous signal?
Don't have any range between the values. Like from start, there is no range in the data.
Okay, and anyone else? What is a continuous signal? Very simple. Any signal which is continuous over time means there are no jumps in between. So you can see the signal, it has value at each and every time. So you can see you have value at 1, you have value at 2, but you also have value at 1.0001. So any signal which has value at each and every time instant is called continuous signal, right? And normally in real life, most of signals are continuous signals. And on the other hand, you can see that we have a discrete signal, or we sometimes say digital signal. So you can see a clear difference. So it has value at certain instances, and this signal doesn't have value in between. So you can see that it has value at 1, but if you want to find value at 1.5, you don't have any value. It means that discrete signal has values at discrete time intervals. So whatever discrete time interval you have chosen, it has value at those specific instances. And both of them are equally important. We'll see later on that this analog signal or continuous signal, this is something that we have in real life. But maybe for computers, you all know that computers understand digital language, 1, 0 in the form of bits. So that's why for computer this discrete signal is useful. So it is important to understand both. Then we have periodic signal. Definition, anyone, what is a periodic signal?
Changes within a period or something like that.
Anyone else? What is a periodic signal?
Is it like a repeating signal?
Yes, repeating signal.
Like cyclic?
Yeah. So a periodic signal is any signal which repeats after a certain amount of time. For example, if you talk about week, it repeats itself after 7 days. If you talk about a year, it repeats itself after 365 days. So it means that the time span is 365. If you take, there are two examples. One is sawtooth. You can see that it starts with some value of -1, it goes up to 1 and then comes again and then starts again. So here you can see that if we talk about time period, this is 0.02, again the difference here is 0.02. So it means that this sawtooth waveform has a time period of 0.02 seconds. So it means that it repeats itself after this much time interval. Now there is another example you can see is a square wave. Again in this case, you are going 1, then it's coming to -1, and at this point it is repeating. So again your time period is 0.02. And this kind of signal is normally used in power system, also used in digital logic design, because if you want to turn on any gate or any signal, you want to give 1 or 0 signal, sometimes +10, -10, 0 or 5. So these signals are useful for such kind of application where you want to turn on or turn off something. So here is example 1 and -1, but there are other examples as well, 1 and 0, 5 and 0, and so I don't know why 1 and 1, this is not 1 and 1, 1 and 10. But you, in any signal which has two levels is a square wave, and you will later on see that what are significance of a periodic signal. you will see it is easy to visualize, it is easy to analyze periodic signals, and at some point, if you have a signal which is not periodic, you forcefully make it periodic, because most of the techniques which are developed are for periodic signals. Then here comes another example. You can see that in this case, you can see that we have, is it periodic?
No.
Why? Why it is not periodic?
Not repeating.
Not repeating, right? Because it starts from 0.02 ends at, no, start from 0.01 and ends here, and it is not repeating itself. So it means that this is not periodic. This is called an aperiodic signal, which doesn't repeat itself. And similarly, you have another example for a rectangular wave. Again, this is not repeating itself, so these signals are attributed as aperiodic signals. There is another example which I introduced when you have seen similar example when it was a continuous signal. So now, anyone tell me, this is periodic or not? Number one, is it periodic? And number two, which one is periodic, which one is aperiodic? What is the definition for periodic signal? Which repeats itself, right? It means that repeat with the same amplitude. Everything is same, it's just that it repeats. For example, everything remains the same and repeat itself. So, is it periodic?
No.
No, it is not periodic. Why? Because you can see that if you move toward left hand side, it is damping, it is nearly going to zero, and if you move toward right hand side, again it is going to zero. And this is the mathematical equation, and from this equation we somehow know if we put this time as infinity, so e power minus infinity is zero. This is an identity that if you put minus infinity to anything, it comes as zero. And how it is done? So if you want to bring it like this, and 1 by infinity is always equal to 0. So it means that theoretically this signal will go to 0 at infinity, but looking at it, it is aperiodic because it keeps on damping if we are moving away in the time. Now there is a more or less similar example, but there is another function which is called sinc function. So if you define a sinc, have you ever heard about sinc function? So in case of sinc function, its definition is that it is this is sine t by t. This is not c. This is sine t by t. It means that if, for example, you are putting time equals to 0, then you divide it with 0, then 1. So if somehow we plot it, it comes out as this signal. And there are two equations for the same signal because some books donate sinc function with the equation number 1 and some donate with equation number 2. But overall, you can see again that this is not a periodic signal because it is not repeating itself. There is another example of the signal which is useful for communication or for mobile purposes. Have anyone heard about VCO, voltage control oscillator? Somewhere, right? So in this case, what happens that when we are transmitting a radio signal, you might have radio in your mobile phone, so we do different kind of modulation techniques which are called FM modulation, AM modulation. Not part of this course, just introducing you to various kind of signals in different domains. So what happens in this signal that you want your frequency to change with respect to voltage. So in this case, the first one is VCO triangle. You can see that it starts with 1000 frequency and go up to 4000, then comes again and so on. And similarly, we have another signal which is a rectangular signal. So you have a constant frequency 4000, then it goes to 1000, keeps here and so on. And such signals are needed in FM modulation and in other communication and telecom systems. So these signals are very common. Now, is it periodic or not?
Looks like periodic.
Periodic. What is time period?
1.
1. Anyone else? What is time period? What is time period? Definition for time period. The time after which it repeats itself, right? So where it is where this signal is repeating itself? At 1, right? After this, the same signal. And where this signal is repeating itself?
After 1.
Yes.
After 1, because positive, negative, and then again positive, negative. So it means that both of these signals are periodic, and we need these signals as periodic. Okay. Then moving a bit further, so that was an example from telecom systems. But if we talk about digital logic design, or if we talk about switch on off, turning something on or turning something off, so we have this pulse train or this called pulse wave. So in this case, what happens that these are normally used for controlling power electronic converters. If you ever heard about, if for example you have, if I'm charging my phone, so I plug it into socket, and then on the other side I get low voltage, right? So that mobile charges itself a converter, and inside converter you have a lot of switches which you want to turn on and off. So in this case, you have an on signal and an off signal. So you can see that it starts here 1 or something, and then goes off and then turn on and off. So here you can see that if I take this interval as on and this interval as off. So the purpose of introducing this signal was to bring you to another terminology which is called duty cycle. Anyone, what is definition for duty cycle?
Duration by time is repeated.
Yeah, you can read it, right? Okay, so duty cycle is, before duty cycle, is this signal periodic or not?
It's periodic.
Yeah.
It's periodic, right? Because it's repeating itself. So now it means that, and as I said, periodic signals are easy to analyze. Why? Because we can take only one cycle and analyze it. We don't need to worry about other cycles because all of them are identical, right? So here it means that this total place is T, which is the whole time period, right? And in this whole time period, for tau time, this signal is on, and for all other time, this signal is off. So on time divided by total time is called duty cycle. Mean for how much time this signal is doing a duty, is turning on something. So this is called definition for duty cycle. So what is duty cycle for this signal? What is on time here?
1.
And what is total time?
4.
So duty cycle would be 1 by 4. And normally duty cycle is measured in percentage. So if someone say that this switch has 25% duty cycle, so you will clearly know that for 1/4 of its time it is on, and for rest of time this switch is off for some reason. So that's why these signals are important, because these signals are used in every application. In power converters, in digital logic design, TTL, everything, at every place where you have a switch, these kind of signals are being utilized. Now finally is speech signal, the most difficult signal and the most complicated signal to analyze. Why is it most complicated? Because each time it is changing in amplitude. So if I'm speaking loudly, it has high amplitude, slow amplitude. Each time the frequency is also changing with which I am speaking. Maybe you want speaking with different frequency, different amplitude, different pitch. So these are the most complicated speech signals. And an example for
Siri and Alexa.
yeah, Siri or Alexa, speech processing, right? So this is a good example. Any other example for speech processing?
Google Assistant. I don't know.
Yeah, there is one written here as well. There are live events. So you might have seen that if, for example, you are watching a live football, you also see that there are subtitles. So what's happening that it's reading those speech signals and then spitting out the subtitles. But it is you will always see that those are a bit laggy, because once the speech is done, then it will be processed and then it will come out. But these days we have so much good algorithms that those are done easily. But overall, speech signals are the most difficult signal to process because of their varying attributes. Okay, This brings me to another type of signal. Like I said, the speech signal is the most difficult, and sinusoidal signal is the most easy signal to process. What do you think about a sinusoidal signal? I know most of you will know about the formula, but what are your feelings? What do you think a sinusoidal signal is? What is its significance? Why it is important? Who have studied circuit analysis? I can remember you, right? You have studied circuit analysis, right?
No, not me.
Okay.
So
No?
there's just like different points, there's different voltages.
So tell me again.
Different points of the way, there's different voltages.
Okay, yeah, this is one point. Yeah. Any real life example where you have seen sinusoid? I have mentioned so many times in my lecture as well, but yeah.
Unfortunately, we haven't attended any of the lectures.
No. I just mentioned that. What is a sinusoidal signal? What is coming from this socket? The AC socket where you plug. It is a sinusoidal signal, right? No? Okay. Yes. So sinusoidal signal has its significance because whatever is flowing in these transmission lines, all the electricity, it is a sine wave. It is varying with time, so that's why sinusoidal waveform is very important. And there is another reason for its importance. If I have sine theta, what is derivative for sine?
Cos.
Cos, right? And what is integration for sine? Again, minus cos or something, right?
Yeah.
Again, this is something cos. So it means that if you take if you differentiate sine or if you integrate sine, it is still a sine function. Cosine and sine are same. It's just 90 degrees shift between. But theoretically, you can say that they have same structure, everything same. It's just that if I draw two signals, so sine is this signal, and if I want to draw cosine, so if I start a bit before the 0 point, but they are identical. So it means that if you differentiate a sine signal, it is still sine. If you integrate a sine, it is still more or less sine. So it means that sine signal is the most stable signal, and it is the most fundamental signal. And in our later weeks, you will see that this sine signal is base for every signal. It is a kind of, I have written a word block of Legos. Why? Because with those blocks you can create anything, right? So if you have sine and cosine signal, you can write any signal using these. So if, for example, if I want to convert something happening in the laptop, is there any signal? Or if this heater is, if I'm giving power to the heater and it is generating heat, I can write this signal into sine and cosine. So that's why sine and cosine are useful, because everything in the world can be written as a combination of sine and cosine. And this is called Fourier analysis, which is one of which is huge part of this module. So that's why it's very important that we learn about sine and cosine. And this was actually originally proposed by a scientist called Fourier. However, when he proposed this thing, there was another mathematician, Lagrange. So he opposed him. And he, because Lagrange was at that time a big mathematician, and when Fourier said that he can write any signal in sine and cosine, and literally everyone was laughing, and he was rejected. And unfortunately, Fourier died. He never knew that now we are using Fourier series. And later on, it was accepted that yes, Fourier series is enriched, and yes, every signal, even human body, everything can be written in terms of sine and cosines. So that's why it is very important that we understand something about a sinusoidal signal. If we quickly go through the equation, it says that y of t is equals to Vm sine of omega t. So this is a very typical equation for a sinusoidal signal. Now what we have here, Vm is the amplitude, omega is the frequency, angular frequency. Normally, as I said, that we have 50 hertz, right? That 50 hertz is f, which is normal frequency in hertz. But when we are talking about sinusoid, it is referred to as angular frequency. So this omega is equals to 2 pi f, and this f is, as I said, this is frequency and it tells us about the repetition of a signal. Now, if you have a look on the sinusoid, you can see that it has this amplitude going up, positive side, positive Vm, and negative Vm. So this is typical definition for a waveform for a sinusoid. Now, you can see that, is it periodic or not? It is of course periodic, right? Because sinusoid is the most typical example for a periodic signal. So it repeats itself after this time. So we can say that this is time t. Any time after which it repeats itself is called time period. And there is another good relationship that time period equals to 1 by frequency. So from frequency, we can get to know that after how much time it will repeat itself. The power, the voltage that is coming from socket, as I explained previously, is 220 volt, 50 hertz. So it means that in this case, frequency is 50. I can easily find time period, which is 1 by 50. So it means that if you want to see the sinusoidal signal on oscilloscope, if for example your oscilloscope is between 0 to 1 second, you will see a lot of pulses. Why? Because it has so much less. I'm not sure how much, but it could be 10 millisecond or something, or 9 millisecond. So it means that within 1 second it will repeat 50 times. This is what a definition for frequency. This is the number of cycles the waveform completes in 1 second is called frequency. So if a signal has 50 hertz, it means that within 1 second you will see 50 cycles. Okay, so if the periodic time of a waveform is 100 millisecond, how many cycles per second does it complete? So here you can see that it says about time period, which is 100 milliseconds. So what is the frequency?
1 by 100.
1 by 100, right? And if you have a look on this waveform, how many cycles can you see?
How the full cycle?
Yes, how many full cycles here? 1, 2, 3 and half. So it means that in this thing we have 3.5 cycles. So yeah, this was just a very quick example, but the overall concept about sinusoid is that you have positive half cycle, you have negative half cycle, you have time period, you have frequency. This brings me to a bit modified version of a sine wave. So previously we were not having this extra term and this extra term. And you can see that if you have a look on this waveform, it starts from 0 and repeat itself. Later on we will see that where it repeats, but yeah. It starts from 0 and then moves on. But that one was pure sinusoid. But we can modify it. We can shift it either in x-axis, move it left or right, or we can move it up or down. So here is the equation. So this phi, when you are adding something to the angle of sine, it will shift your sine wave either to left or right. However, when you are adding something to this whole equation, it will shift your signal up or down. So this VB is called DC bias, meaning it will shift. If this is 0, it means that your sinusoid will start from 0. But if, for example, this is 5, your sinusoid will start from 5. Okay, so here is the example. So you can see that in the first example, this is A sinusoid equals to AM sine of omega t. So this is the same as previous. So you have AM plus, you have AM minus, and it is started from t equals to 0. Then in the second case, you can see that we have added plus 5. So when you are adding plus 5 plus phase difference, it will start earlier. So that's why you can see that this waveform is shifted towards left and it is starting a bit earlier. Same goes for the other side. So in this case, you have added a negative angle. So when you are adding a negative angle, it will start later. So that's why you can see that it's starting from here. And since it is periodic until infinity, so the same will repeat on the left and right hand side. So that's why if you're adding this phi, which is phase angle, it can shift your waveform right and left depending on the its value, whether it is positive or not. However, we can also shift this waveform up or down depending on this bias value. Again, you can see that this blue signal, it was starting from 0 and going somewhere. However, in the second example, you can see that we have added nearly 0.5 to it. That's why you can see that if I use this equation, which is Vm sine of, at time t equal to 0, this would be 0 plus, okay. So for this example, we don't have this phi. Phi is 0 in this case. So you have sine of 0 plus bias, which is 0.5. So sine 0 is 0 plus 0.5. It means that at time t equal to 0, it will start at 0.5. So it means that it is shifted 0.5 up. And same thing goes for all the other points. So your whole waveform will shift up. And if you add a negative value here, so again, if you start with t equal to 0, 0, and if there is a negative value, your waveform would, the green waveform would start from here and go like this. So it means that you can shift your waveform up and down by adding the bias value. However, you can shift your waveform right or left depending on the sign of the angle. Okay, so here is an example. So the same example is extended. You can see that we have two signals. One is 5 sine of omega t. So if we somehow draw this signal, what would be the peak amplitude? What would be the maximum value for this signal?
1.
Or 5.
5, right? Anything which is multiplied here goes to the maximum value. And then we have a second signal. In this signal, you can see that this is same as 5. However, you have added DC bias, as well as you have added this phase shift, which is pi by 2. So in this case, you can see that if we have a look on the first signal, your first signal is a pink one, which is starting from 0 going to 5. However, if you look at the second signal, so the second signal is not going to negative. Why? Because if we talk about only this is fluctuating between plus 5 and minus 5. But when you have added this 5, it means that the minus 5 becomes 0. So your waveform is completely shifted to up. So it means that in the yellow waveform, you don't have a negative polarity. So we do need these kind of operations. Sometimes you do have negative signals, but your device is not capable to hold negative signal. So in order to process them, you do intentional DC bias, and once you're done with your analysis, while giving it back, you reverse the bias. So we do all kind of analysis to make our analysis easy. Any question on this? Any confusion?
So if you just add 5, you just shift it up, right?
Yes, if you just add 5, so this will go exactly, it will start from 5 like this. But in case of yellow, you can see you have shift as well, right? Then it will be no shift. It would be exactly this waveform starting here. Yes. So, but in this example, we have shift plus DC bias. Now, we move to another important concept. Like I said that in our real life, every signal is analog. There is no digital signal in nature. So take an example of temperature, so it is varying all the time. So it is a continuous signal. If we talk about sinusoidal waveform, if we talk about speech signal, anything, there is no signal that is digital. However, for processing it, we need computers. We need some device which doesn't understand analog signal. So it means that to bridge this gap, we need to have something to convert this analog signal into digital signal, and once we are done with the processing, to convert again a digital signal for someone to understand in real life. What is an example? A good example is that if you want to control room temperature, so what you're going to do, you're going to install a sensor. Sensor is generating an analog signal, and you're going to compare it with a set value. For example, you are saying maintain temperature at 25. So that analog signal will be sent to computer via analog digital converter. Inside, it will measure, for example, if temperature is low, it will generate a signal which will come again from digital to analog and would either turn on heater or something. So it means that we need this intermediate bridge, which is called digital to analog converter. So in terms of converting an analog signal, we have certain predefined steps. So, but before moving to this, are you clear about a continuous signal and a digital signal, right? It means that computer understand digital values in form of bits, whereas natural signal is a sinusoidal signal. So it means that we need to somehow convert this sinusoidal signal in the form of bits. I will come to this later, but in the form of bits. So for that, there are a few steps. Okay, so for this we need a circuit. Since this analog signal has infinite values, but we cannot take those infinite values. So it means that we need to take values at certain points depending on the processing power. So it means that we will take one value, then we will wait, then we will take another value, wait, then we will take another value and wait. So it means that we need a circuit which can take certain value, hold it until the next value comes in. So it means that we need a sample and hold circuit. What is a sample and hold circuit? Consider a very basic example is about a capacitor. So you have a switch, you have a signal. So you turn on the switch, the signal goes to capacitor and generates some voltage. And then you close the switch. Until the switch is turned on again, this will be held by capacitor. So now consider this example. So you have a sinusoidal signal or any signal. Then you have at these instances you want those samples. Like I said, that we cannot take infinite samples. So we need to decide the sampling frequency, that how much samples do we need. So in this case, 1, 2, 3, 4, 5, 6, 7, 8. So for this we are taking 8 samples in one cycle. It depends on your requirement, how many samples do you need. Less samples are good or more samples? More samples are good. So as to exactly imitate the actual signals, right? But at the same time, from a computational point of view, more samples are bad. But we need sometimes we need to do a trade-off, whether we want quality or whether we want low computational power. It depends. So in the start, you can see that there was no on signal for the switch. So you have 0 coming here. Then at this point, you turn on this switch for a while, and for that while, you can see your voltage was this. So this was your voltage for this instance, and same you can see is held by capacitor. This means that the capacitor started charging from this point and reached here. Now your switch is off. So it means that now this capacitor will hold its value until the next sample comes. So until this point, you can see that it is holding its value, and now here you have again another pulse. And when you have another pulse, you have again small voltage, which is again sample. So you can see this is a small, when you will look at PDF closely, you will see that this is a small pulse. And then again, since it is off here, it will hold it again. So, and so on. We will repeat this process, and we will be taking samples. But still you can see that this signal still looks somehow analog, because still it is not in the form of bits. It is somehow continuous. But there is one thing that now you have certain levels. So you have 0, you have this one level, this. So you have certain levels. So it means that the very first step was to sample and hold your signal, which is done. Now the last step is you will send this signal to finally bit conversion. You will convert or you will assign it to certain bits. So for example, I say, okay, if this is 0, represent it with 0, 0, 0 bit. If it is this voltage level, represent it with certain bits. And now you will understand that in terms of logic design, we are always limited with number of bits. We cannot use infinite bits. The more bits we use, the more registers we are using, and ultimately increasing the cost. So it means that the very first step was to take your analog signal, sample and hold it, and this is clock signal, which is the gate signal or turning on switch on and off sample time. This is your analog signal segment, which is the loss signal, which I said that is still analog but with some samples. And now finally comes this ADC, which is taking this segment signal and transforming it into number of bits. Okay, so that's why we say that if you have an analog to digital converter, I will now go into next slide where I will be explaining that how this works. But overall, you have an analog signal, and then finally you have digital signal, which is in the form of bits. And if we talk about the opposite of this, so you have this staircase signal. So you have all these levels or bits coming in, and then you're converting it to an analog signal. So the same bits, like I said, that each bit represents a level. So you can take this staircase and then we do some kind of filtering to make it smooth. But this is the process. So imagine that this red was different levels. It was a segment signal that we have just studied. So 0, then this was considered as one level, considered as another level, and so on. So imagine that we have this signal here, and we want to represent it. So this was your original signal, which is from 0 to 5 volt. This is an analog signal, and we want to convert it into a digital signal, right? So the very first step again is to sample and hold, right? But the next thing is to decide which analog to digital converter you are using. Whether you are using 3-bit, whether you are using 4-bit, 8-bit, and so on. The more bits, the more closer it is to your original signal. So in this example, we have 3-bit analog to digital converter. It means that 3 bits mean 2 power 3, 8 levels. If you remember from DLD, so you write 0 1 0 1 0 1 0 0 1 1 and so on. So this is how you make a table. So it means that if you have a 3-bit analog to digital converter, it means that you have 8 possibilities. It means that you can map 8 voltage levels with 3-bit converter, right? So it means that whatever is your input signal, it can be split into 8 levels, right? So it means that you have infinite number of points, but you are limiting them to only 8 points for that. Okay, so in this case, since your input signal is maximum 5, so it means that we need to accommodate that. So total you have 8 levels, and your full signal is until 5. So each level can be 0.62. So your maximum voltage is 5, and the level that you can take is 8. So if you simply divide your maximum voltage with your number of levels or number of levels that you can present, you will see that each level corresponds to 0.625. What does it mean? It means that if there is anything between 0 and 0.62, it would be one level. It will not differentiate. If it is 0.3, still it is 0. If it is 0.6, still it is 0. So it means that anything that will come below 0.6 threshold will be taken as 0. Now you see that with 3 bits, you are compromising a lot. Although 0.6 is not 0, but since this is a low bit converter, so that's why you are compromising on the quality. So when you will convert this signal with this analog to digital converter, until 0.6 you are considering it as 0, which is somehow an error, right? Similarly, then from 0.6 to to its double, you will be labeling it with this level, and so on. So it means that we have 8 levels. We move from this point until certain point, and we are representing our signal. So what does it mean? It means that we are converting our signal, but our quality is compromised. Now, if for example, you understood this, right? Any questions on the table?
Yeah, I think I have a question. Do you know how to define a 1.025? Did it times in 0.621?
0.62 plus 0.62.
Okay, plus them then now.
Yeah, because each level, the difference between each level is 0.62, 0.62. So to each level, you keep on adding 0.62, and this is how you will reach to 5, because our end goal was to reach 5. Okay. Now, if for example, we could have taken 4-bit. With 4-bit, it means that 2 power 4 is 16. It means that now we can represent our signal with 16 levels. Now this is a bit better. Why? Because each level is 0.63. So it means that between 0 and 0.3, everything is 0. Then between 0.3 and 0.6, everything is 2 and so on, right? So it means that now the representation is a bit better than the previous one. Any question? Fine, right? Okay. Now that was example for analog digital converter, but like I said that we need that converter to give something to computer, process it, but once it is processed, again after processing or doing anything, computer will again save it in the form of bits. So it means that we again need a digital to analog converter to reconvert it. But it is very important that the analog digital converter and digital to analog converter, they must be having same number of bits. So as to have accurate reconstruction. Okay, so one of the example here is weighted summing circuit. So what does it do? You take each bit, because in the previous case we have seen that each level we are representing with certain number of bits. So consider that we were representing them with 3 bits like in the previous example. So we will take each bit, then we will give it to an op-amp. I will not go into this detail that how this op-amp works, but if somehow we write equation for output equation for the op-amp, this is minus times Rf by R1, V1, V2, Vn. So it means that if we choose some right values for the resistors, we can convert those bits into corresponding analog value, because you can see that if for example this was 1, this was 0, this was 0. So it means that this is 1. So Rf by R would decide some number. That number will be your output analog signal. We will be covering example on this. But like here you can see that if we choose certain number of values for the resistors, then we come up with an equation which we can use. We can input each bit and we can find the final value. Here I have taken an example for 4-bit converter. So in this case, you can see that we have VA, B, C, D. So what is VA, B, C, D? VA, B, C, D. 0, 0, 0, 0. So imagine that the analog to digital converter was a 4-bit, and then when you are reconverting it again, you have to do it with a 4-bit. Then you have to decide something on the resistors. So normally resistors are decided starting with a 1, then you multiply it with 2, 2, and 2. This is how we do it. Why? Because you know that this is 2 power 0, this is 2 power 1, this is 2 power 2, 2 power 3. So that's why we use same weighting for the resistor. So, okay, so this is the other way around. So this is A, B, C, and D. Okay. So that's why we have 1, 2, 4, and 8. Why we have done this? Because it is coming from the bits values. This is how we do in DLD, digital logic design. So 2 power 0, 1, 2. So the same things will come here, because these values are originally coded using the same pattern. So now we're using the same pattern in terms of resistors. And like I said previously, that now the op-amp equation would be, since we have 4 inputs, so the very first one was Rf by R1, so it is 1 by 1, 1 by 2, 1 by 4, 1 by 8. And sometimes this converter is also called 8421. Yeah, sometimes this converter is also called 8421. Why? 8421. Because this is a 4-bit, so the first 1, 2, 3, 4, so that's why when we are reconverting it, we are using the same values for the resistors. So let's take this example, which will explain to you. So now we have signals in the form of bit that was processed by computer, and we have all those bits, but we want to see how much, to what value it corresponds to in the analog signal. So we are taking these bits, we are using this equation because we have just learned that we can use weighted summing to convert a digital signal into analog signal. Okay, and then the final output would be in volts. Now these bits can be 1 and 0. This bit can be 5 and 0 depending on your microcontroller or anything which is generating output. Typically, when we say 1 logic or 0 logic, it means 5 volt or 0 volt, but it can be different for different devices. So let's take the first example. So, okay, so like I said that 5 is the 1 logic and 0 is the low logic. But in this case we have put everything 5 and then we will be multiplying it with 0 or 1 to understand it better. So you can see that the first case everything was 0, so the output volt is 0, which is what we have represented it earlier, right? Then starting with the second bit, so 0, 0, 0, and this last bit will be multiplied. So again, which is right, which is 0.625, and then we keep on going. And since this was the 16, so this conversion, sorry,
Level up.
yeah. So this is 2 power 16, right? So previously, what I was telling you, in this case, the maximum value was 5. So when you were converting it with 3-bit, each was 6.25. When you were converting this 5 volt with 16-bit, each was 0.31. But if this is 10 volt, then the case is different. If it is 10 volt, so 10 by 8, and similarly 16 by 8. So 16 by 8 you get 0.62, and this you get even a bigger number, right? So it depends on two things, the number of bits and the maximum voltage that you want to represent. So in this case, the maximum voltage that was represented in actual case was 10. So that's why the difference between the levels is 0.625. Still, although we are using 4-bit, but previously with 4-bit the maximum was 5, so that's why the levels were small. But in this case, since the voltage is higher twice, so the levels are still unchanged. So that's why you can see that these are the representation. There is another thing that no one noticed is we have a negative sign here, right? So it means that whatever we are getting at the output is minus of the actual signal. Why? Because this is because of op-amp. Because if you have you ever studied op-amp? I believe yes, right? So, sorry? Yeah. Yeah, so you have inverting, so if you use inverting terminal, you use non-inverting terminal, depending on that, your output varies. So in this case, your output is negative, but you know it is positive, so you deal with it accordingly.
Electronics is bad.
Any question on this? Right. Okay, before we go forward, we have another important thing to understand, because this will be used heavily in our all the lectures. Do you know how to calculate an average? Have you ever calculated average? No, mean value, right? If, for example, I say that I'm traveling with 20 mile, 20, if I have 3 values, or if, for example, I say that 20 marks were achieved by 3 students, so how much is the average? So I divide it with 3, and then I get average as 20, right? That means that it was a good average. So this is how we normally calculate average. But if you have certain data. But if you have a continuous signal, again we do the same concept, but instead of summing it manually, we use integrals, right? What integration do? It's sum. So it means that if you have a Y signal which you want to find an average, so there are two steps. The first step is to sum it, like we have done it here. We have 3 students and we want to find average. So we have some marks for each student and then divided by the total number of students. So here in this case, if you have a signal, if for example this is a signal, I have to sum each and every point. And then I have to divide it with the total number, right? So that's why we say that we integrate signal from 0 to t. This is for a periodic signal. As I said, that periodic signals are very easy because we only need to bother about one period, and for the rest it's the same. So total, we are integrating it and then divided it with the total time period. So this is how we get average. So sum it and then divide it, so you get the average for the whole period.
We allow process.
Yeah. So now here is an example, a quick one. So we have this signal here. Is it periodic or no? Periodic, right? So you can see that we have this signal which starts from 0, it goes to D and its amplitude is A, right? And then from D to 1, its amplitude is 0. That means that this is a periodic signal whose time period is 1, and then it has value from 0 to D, which is A, and then from here to here, it's 0. But when we want to find an average, how are we going to do it? We will write that 1 by D, 0 to D, x of t. So now we need to split it into two parts. One is from 0 to D, so that's why we say for time period we have put 1 because the time period was 1. Then from 0 to D, what is the amplitude? The amplitude is A, right? What is the value of the function? So from waveform, what we normally do, because here we need value for the function, so for certain time period we need to see what is the value of the function. So here from 0 to D, this is fixed, which is A, so that's why we put A dt, and then from D to T, which is this point to this point, you have 0. So it means that this term will go to 0, and we left with only this term. And who's going to solve it? How are we going to solve it? Anyone can solve it. 0 to D, A, dt. So how are we going to solve this integral? This is very basic, very easy, right?
Just add 1 divided by just add 1 to the power divided by the thing.
But this A is not function of time, right? This is constant.
Oh.
So we need to take A back. 0 to D, 1 dt, right? And we know that integration for 1 is simply t.
Yep.
So we write A, t, 0 to d. And we need to put these limits only on t because this is time variable. So how are we going to put limits? So we write A, and inside upper limit, d minus 0. So finally it would be A times d.
I have a question. Why did we break it up again?
Why? Okay, so we need to, in average, we have to average it over the whole time period, right?
I get that, but even if it was just not average, just an integral, why not do it in one go from 0 to t?
Okay, good. Now, the question is good. We cannot do it in one go because the function is not same for all,
Oh.
right? So if for example this was t, then it is fine. We can go in one go. But here you can see that there is a break. So for this portion of the time period, remember duty cycle. So for this time it was on, but for this time it was off. So it means that for this time you have some value, for the other time you have 0 value. So and inside this integral we need value for the function. So if within one time period the function has two values, so we have to integrate for both of them separately. We cannot do from 0 to t, because if for example I am doing 0 to t a, this would be wrong because function doesn't have a value from 0 to t. It has a value but from 0 to d, and it has 0 value from d to t. Any question on this?
So, yeah, on that second part of that formula there.
Yeah.
If that line was down below, it would just be minus whatever, would it? Yeah.
Precisely, yes. If for example,
Or
yes,
up,
good.
it goes plus.
If for example it was like this, and it was minus a, right?
The
So
second
what
bit
we
is just for the-
what we have done here, so it was d to 1 minus a times dt, so it would be minus a d to 1, sorry, this d, minus a upper limit minus lower limit. So this should have the answer if the waveform was on the negative side. Yes.
So that's for the on, that's for the off.
Sorry,
That's for the 1, that's for the 0, in terms of voltage.
let me sorry.
So that's like for the positive part, when it's flat,
Mm-hmm.
that's the second part.
Yeah, that's the second part. But when you write average, you need to write them together. So you can
Yeah.
see that here they are together. Although I have solved it here,
Yeah.
and this part I have solved separately. But at the end of the day, I have to write it together. So for the original function, it was supposed to be like this, AD plus 0. But if, for example, the function was going towards negative side, then I have to write it here. Any other question on this? Okay, so find the average value for this signal, please. Do it in your notebook. So the signal is y of t equals to 10 to the power minus 200. And the time period here is 0.05. And I will go back to
Question again?
Question is that you have to find average for this signal.
You need E
So it's like
This is 2 minus.
it's a
10.
no, it's like
Signal for e power
exponential
Yeah.
but negative.
I don't remember.
e
how
power
it's called.
minus
to the power
200 t.
e to the power x function.
Oh, e something like that.
Yeah, it's e to the power x function.
Yeah, yeah. But if it's negative,
It'd be
is it like this?
yeah.
Or
Sure.
is it like
No, no, it should be like this. Yeah.
So integral for e power minus at equals to e power minus at.
What is it?
So just start putting everything in the formula. So you have your time period, which is 0.05, so 0 to 0.5, and in place of x of t,
Anyway,
you have to write this
have the
function.
graph. There's no need to find the graph yet. I guess. T is big T. I T revert. 1%. Is this small T? What was that?
Power minus 200.
t? The small t is like
200.
like the x.
and it's
Oh, the
minus
x.
2. Minus 2. This is minus 200.
The integral of e to the x.
You have to get your hands on mathematics because there are a lot of mathematics coming up.
Yeah. Not the integral at the x is still at the x. That's
Yeah.
what I remember.
Yeah. And so
What is the final answer, anyone?
Oh, I got it.
You have to finally apply limits as well. So
Limit? Yeah. But I think I know.
you want the answer?
Just a second.
So your time period is 0.05, right? And then 0 to 0.05, and your equation is 10 times e power minus 200 t dt. So the very first rule for the integration is that if there is anything which is not function of time, take it out of the integration, right? This means that here 10 is not function of time. The only thing which is function of time is e power t. So you need to take 10 out. So it would be 10 divided by 0.05, 0
Questions I'm still
to
working.
0.05 e power minus 200 t dt. Now the next step is, since now we have everything out, we can easily solve the integration. And to solve the integration, I have written the formula. So the integration of e power minus 200t is e power minus 200t divided by, you have to take derivative for this, which is minus a. So it's minus 200. And then you need to apply limit to 0 to
Seems
0.05.
nice. The result.
it is. How do you get 1?
Huh?
How did you get 1?
I got
Oh,
Is that one?
no, you're right. I forgot.
You
Is
what?
there anything to the power of 0 is 1?
Yeah.
Yeah, I forgot. I thought it was these.
See? It's not it. No. I think. Something. You have a calculator.
Now, before applying limits, again, if there is anything constant, just take it out. So here, this term will become 200,
I still
and in the denominator is minus 200. Inside, you will be having minus 200 t, and you have limit 0 to 0.05. Now you are good to apply limits.
I cannot simplify more.
Do this,
Yeah.
and then all of that's just -1.
So it means that this 200 would be cancelled by 200.
Yeah.
This will turn out as
Minus.
Yeah, I got -1 as well.
minus 1.
Yeah.
And,
And then
if
you
we
just-
going to apply the limits,
Is that it?
it would be
I got
e power
-1.
minus 10
I don't know why.
minus e power 0. So the first thing is to apply upper limit.
Yes.
So
Oh.
200 times 0.05 would be minus 10. So the e
Yeah,
power
my-
minus 10,
my
and the
bad.
lower limit is 0. So anything multiplied by 0 equals 0. So this is your final equation, which is minus 1, and inside e power minus 10 minus e power 0. If you're going to solve it, you will see that if you're going to solve it, you will see that it will become minus 1. This e power minus 10, if you solve it with the calculator, it will come out as very small value. You will see that. I am taking it as 0, and then e power 0 is 1. Anything having power 0 is equal to 1. 1 power 0 is 1, 10 power 0 is 1, e power 0 is 1. So finally, you will get minus 1 into minus 1, which is as 1. I have assumed that e power minus 10 is very small value. I have taken it 0. If you don't take it 0, it will still come very small number, and ultimately you will get 0.999 something, but ultimately your answer is 1. Any confusion on this? So whenever you are solving integral, it's very important to identify function and the integrating thing. So if you are integrating with respect to time, then you need to keep only those functions which are with respect to time and take everything out. If you have two functions, one is function of y, one is function of, let's say, other variable z, and you are integrating with t, then the function which is function of z would be taken out. The only thing that will go into integration is the actual number. For example, here 10 was not function of time, so I took 10 out. The only thing which was function of time, I keep it inside, then take integration, then again take constants out, and then apply limits.
I have a question. Why didn't we break this into two, like last time? With the square one.
We break it.
So the time is.
Let's break it.
Because there is no break part. It says that compute time average having a time period of this person. In the previous case, we broke it because over the time period, its value was changing. But if, for example, in the previous example, we have given that compute y of t a for time period of 1, then we don't need to break it, right? Then we are taking it for the whole period. So here we will not mention that it is broken. It is same function for the whole time period.
It's 0.05, isn't it?
Sorry?
The time was 0.05.
Yeah.
So, sorry, do you mind going over the steps again for me, please? Just like briefly. So you,
It's recorded.
Which one? This part?
yeah.
This one. Okay. So right. So we need to find average, right?
Messed up here.
So the formula for the average is this one, which is 1 by t is 0 to t and your function. So time period was 0.05. It's given here, right? So we just put 1 by 0.05. Then limit is 0 to time period. Again, time period is 0.05, and then we put the function. The function itself is 10 e power minus 200 t. So this was the first step that we have written. Now the next step is to take constants out. Whatever which is not function of time, take it out of the integral. So that's why we have take 10 out, 10 divided by 0.05, and rest we have written inside the integral. So it's 10 by 0.5, 0 to 0.5 e power minus 200 dt. Now we are good to solve the integral. So now we have solved this integral, so the integration for e power minus 200 t is equal to e power minus 200 divided by minus 200. So e power minus 200 divided by minus 200. Again, the next step, take constants out and then apply limits. So we took constant out and then we applied limit. Upper limit e power minus 200 times 0.05, it turned out as e power minus 10, and the lower limit is 0, which is e power 0, right? Then in the next step, I said that if you solve this with calculator, e power minus 10, this is very small number. I take it as 0. So I put it as 0, where e power 0 is 1. And finally you get your answer as 1, right?
Thank you.
The signal processing, how many weeks we're going to cover? 6 weeks?
6 weeks, yeah. He's really worried with signal processing at least, yes.
I mean, we did calculus in past year, so it's been a long time. Kind of
Yeah.
forgot it.
I forgot the
I will try to cover something in the tutorials.
Also, are you going to give us some
Yeah, I don't mind integrals, but I need to revise them.
So
Are you
you
going to give us
That's your-
some
your one.
Yeah, that's the problem.
right?
Because I didn't mind until you
We have a
like
tutorial, we have a workshop session today.
It's easy, I just
I
forgot
was thinking
everything.
to take it as a
but-
workshop, but today I will also introduce you some formulas and things. Just change on that.
It's,
When was the last time you did integrals?
yeah, 2 years in the high school.
No, in the first year.
Yeah. I've got everything. It's like, guys, remember last time?
Okay, who's going to solve this
Those are a
question?
lot of topics I realize. It's going to be fun.
Who's going to solve this question?
Oh, I'm not wrong.
But you gave the answer.
Solve it.
Have to do.
Right? I will do it with you in tutorial, right? Tutorial class. Okay. So there is another important thing, same as average, but slightly different root mean square. Have you ever heard about root mean square?
Yes.
Yeah.
Okay, so in root mean square, I will also tell you the physical interpretation, but before that it is important to understand the formula. Root mean square. So it means that RMS. So if you are asked to find RMS for any signal, there are a few steps that you need to follow. The very first step is to square your signal. You will start from right to left. Then you need to take average or mean. And then finally you have to take root. So it means that this part is same as average, except that the original function is now squared, and then you're taking average, and finally whatever number you are getting, you just need to square root it. So it means that if y of t was your function, you need to square it. Then, so now consider this as a new function. For this function you are taking average, and then finally you are taking under root. So this will give you root mean square. So the physical interpretation is, if normally when we speak about voltages or currents, we normally say 220 RMS. Why we say 220 RMS? Because if you imagine that this is a sinusoidal signal, it has equal positive and equal negative part, right? Because it's symmetrical. So it means that if I want to average this signal, what would be the average? What is averaging? Averaging is just summing all the points. So for example, I am summing all these points, then adding all these points, what would be the average? 0, right? Because it has equal positive part, equal negative part. So it means that if we want to analyze some signals which are symmetrical and periodic, we cannot get the real value out of them, because they will turn out as 0. So for that purpose, we need to find RMS. So RMS, if you are finding an RMS for an AC signal, it's equivalent to the same DC number. So you know that DC is a straight value. If you have a 10 volt DC, the average for it would remain 10 volt. So the same goes for an AC signal. In case of AC signal, the RMS value is the same as of the DC value. If it has a DC value, it would be equivalent to its RMS. Like I said, that it's more or less same concept. The only thing we need to do is to find the square, and then we need to average. So if we are given with this function, v sin of omega t, again a scaling function, right, to solve. Okay, so the very first thing I told you is to square it. So what we have done is, there is a mistake which sometimes is being done. If I want to square it, right, so it means that if I have a and b, so I can write a square and b square. So here in this case, it would be v square sine omega t. Where I'm going to put square? Here or here?
Second one, second place.
Hmm?
The second thing you mentioned.
Second? Anyone else? Anyone with the first?
They should put
Science
mouse
fair.
mouse. They should put.
Yeah, look.
Okay, so this will go here. Why this will go here? Because you are taking square of the whole function. If you are putting that square after omega t, it means that you are just squaring the angle, which is not true. You are taking square of the whole thing. So I will write here sine of omega t whole square equals to sine square at this place. If I am putting square at this place, it means that I am only squaring it. So don't do this, right? This is one of the mistakes that is being done. Okay, so v square sine square omega t. So the first part is done. We have squared our function. Now the next part is averaging it. So it means that we need to average this function. So let's continue. So instead of omega, we can write. So we know about omega is 2 pi f, and we also know that f is 1 by t. True, frequency is 1 by time. So you can put it here. Now the next step is bit not a difficult step, but I'm going to explain these identities which I realize now in the tutorial class, which is important. If we cannot solve sine square directly, there is no integration directly for a sine square. We only know integration if we have sine theta or cos theta, but we don't know integration if we have square here. So it means that we need to convert it into function for which we know the integration. So that's why there is an identity which says that sine square theta is equals to 1 minus cos 2 theta by 2. So from here we can put this identity here. Now you can see that we have two parts indirectly. So we have 1 by 2 and then we have cos 4 divided by 2. So you have two functions. So you can solve these integrals separately, but I will prefer to leave it until I cover the formulas. I was not sure about, I was not aware that I have to cover these, but don't worry, I will cover in the tutorial section, which will explain to you that how you're going to use identities, how to take integration, derivation, so that it's easy for you to solve. And I can go through these questions again. Okay. I guess this is it. Any questions?
Nothing.
Oh, it's tutorial.
Yeah, alright.
We can upload the lecture.